will be given by Professor Jianglai Liu of Jianglai University. We'll be talking about the Panda X experiments and recent results from Panda X2.
就差不多了。我是抓到，比如说荧幕到这边满，至少可以抓到。
Maybe I don't need this. This is not on. I like to first thank the organizer for the invitation. It was very kind, and I'm really one of the experimental anomalies here. And also for reasons of experimental constraint, I apologize I have to come late and leave early. I'd like to talk about the Panda X experiment, which is a xenon-based dark matter experiment primarily in China, and tell you some of the recent news and the project. So everybody is familiar with this. We're trying to solve one of the biggest mysteries in the nature. The beyond standard model physics like to have all these new particles. It turns out there's a special type of weakly interacting massive particle, a special generic class, could very naturally reproduce the observed erratic density, which makes it very attractive. Therefore, this is so-called a weak miracle. Everybody likes it from both directions. And for that specific reason, weak interaction will allow us to be able to do terrestrial experiment to measure such a particle directly, either through direct detection, which I will be focusing on, through collider, or through indirect detection. So the dark matter direct detection is concept extremely simple. So we're surrounded by dark matter particles, and we're just waiting for these dark matter particles to collide with normal matter, namely the atomic nucleus, and detect their recoil signal. And this was realized a long time ago, followed by almost 30 years of experimental effort trying to see where these things are. So let me now focus on the xenon-based experiment, direct detection experiment. Specifically, this is an experiment called a dual-phase xenon experiment. So it's a detector consisting primarily with liquid xenon, but the gaseous phase is also important. It's called dual-phase. There are two main experiments in the Europe and the States. Xenon 100 was a pioneer. And finished in 2012, and now they have a atomic-scale experiment in preparation, commissioning actually. And the other experiment called LUX in the United States, a larger one. Xenon 100 is 60 kilogram, and LUX is 250 kilogram of the detector. You see that the target mass is rather big, of the order of 100 kilogram. This is recently completed as well, and their next phase of a multi-town detector called LZ is in preparation. The reason for dual-phase xenon is actually several folds, but the basic concept is that it's a combination of several advantages, making it super attractive for both making it a larger target mass, at the same time allowing good background rejection. So it's a large target, low energy calorimeter. It has the 3D vertex reconstruction capability, allowing you to do the background rejection. There's also another technical reason that it has intrinsic signal to background discrimination. Lastly, but also very importantly, because the large density, the density is 3, it has a very powerful self-shielding effect. So this is a concept showing the dual-phase xenon experiment. It's a typical TPC, but instead of detecting the electrons, this experiment is detecting photons. So a charge particle interaction will provide both the scintillation, which is called S1 light, and then also the ionization with number of electrons. In the TPC, the electron will be drifted towards the gaseous region and get amplified drift towards the gaseous region, get amplified here, generating the second scintillation light. So we call these light S1 and S2. The two lights will be viewed by the top and bottom PNT array located on the cylinder, which allows you to do the X and Y reconstruction of this event and the time separation between these two flashes of light gives you the Z vertex. Now, the background particle, primarily gamma rays, will scatter with the electrons in this detector, causing electron recoil. And I mentioned the WIMP particle will scatter with atomic nucleus, we call inducing a nuclear recoil signal. And because of the ionization density, of these two different types of recoils is different. In fact, the light photon and the charge ratio will be different. And this is a very important discrimination power for the liquid dual-phase liquid xenon. And also due to this TPC nature, double or multiple scattering events can be viewed by looking for multiple S2 to get rejected. Okay. So such experiments, simple in concept, but extremely difficult because of the weak interaction nature, that the signal rate is very low. At the same time, we're looking for very low energy. Even more is because of environmental background. Everything, we are surrounded by gamma rays and the cosmic rays. Therefore, to do such experiment, you have to really hide underneath the mountains to do this, to shield the cosmic rays. Most of these experiments are deep underground. Even deep underground, you still have all the gamma rays from the environment, so you also have to cover the detector with very heavy shield. So this is the location of the underground lab. This is viewing the map of China. This is Shanghai, Taiwan, and this is Sichuan province. The south of the Sichuan province, there is a river called Jianglai River. Goes from the north to the south, making a U-turn at this mountain called Jinping Mountain. This area, the top of this mountain is 4,000 meters high. Because of this very complicated detour as well as the terrain, this area is very rich in hydropower. So along the Jianglai River, there is a hydropower company built a huge dam, 300 meters tall, to generate hydropower. And in order to build this tunnel, to build this dam, they built tunnels through this Jinping Mountain, which is illustrated here. This is a mountain, and the tunnel of 17 kilometers long. Okay? It was existing before the underground lab existed. And the overburden from the center to the top is 2,500 meters of marble rock. And starting from 2009, the hydropower donated a small area and call it the China Jinping Underground Lab, so that physicists can go in and do experiments. Tsinghua University in Beijing led one of the experiments in germanium, and SGTU led another experiment in liquid xenon. And this is by far the deepest underground lab in the world. So now let me give you in one snapshot what is the Panda-X program. So we love pandas, but then the Panda-X actually means the particle and astrophysical xenon detectors. Astrophysical is dark matter, particle is neutrinos. We also like to do a neutrino-less double beta decay with xenon 126. So this is experiment all based on xenon. So we developed this program from scratch essentially with several phases. The first phase, Panda-X1, is a 120 kilogram pancake-shaped detector, a dark matter experiment, lasting for about 5 years, starting from 2009 to 2014. Shortly after this, we upgraded the detector to a 500 kilogram liquid xenon detector, and which will continue run until 2018. And so this is right now the largest running experiment, dark matter experiment in the world. And then in the future, we will upgrade this half-ton detector into an X-ton detector called Panda-X X-ton. Immediate next phase will be roughly a 4-ton scale experiment. And in the future, we are considering even larger. In the US, it's called G3 experiment. Eventually allow us to see the neutrino background. And in parallel, to reflect this particle nature of our experiment, we like to build a detector, another TPC, but with gas, with high pressure gas, to look for the neutrino-less double beta decay from xenon 136. Okay? And the R&D just started this year, and we also have the conceptual design report for this project posted on the archive. This is a rather small collaboration started in 2009 with 50 people, and now we have about 80 institutions in China and a few institutions internationally. So one of the milestones for the experiment is that we develop things off-site, and everything get moved to the experimental site in 2012, but then followed by a very lengthy putting together and assembly and the commission. This is showing the apparatus in the Jinping lab. You see, everything you see here is the shielding. Layers of shielding. This is 3.5 meters across. This is a cryogenic system. So the shielding actually has several layers of polyethylene, lead, polyethylene, and copper. And what you see, the cylindrical piece in the middle, and that's our outer vacuum jacket. And the new liquid xenon detector is actually inside this outer copper vessel. Let me just give you one slide about the Panda X final results. And this was published in 2015. And we had in total 54 kilogram fiducial with 80 days exposure. And in this experiment, it was background limited. However, we were able to lower the trigger threshold. So among the 3 xenon experiment at very low mass, we were competitive. The other thing is, you see this figure is the cross-section versus dark matter mass, all the exclusion curve, but also at that time there were claims of suspicious events, which have formed these contours on this figure, and our experiment did strongly disfavor all previous reported claims. And then we upgraded. So this is the Panda 2 detector, and there was a factor of 4 bigger. Also include number of technical improvements with lower background and better performance, which I will not get into details. We'll just show you some pictures in actually late 2014 when we put the detector together at Jinping. So this is actually what's inside of this is what we call the central region, or the drift cage, the drift cage. The electron will be able to drift in this region. You see the top PMP array, and these are actually the homemade electrodes providing electrical field to the liquid and gas. And this is the backside of the PMP array. This is a specially designed basis. This is putting everything together. And this was actually also late 2014. You see the detector in comparison to a human being. And we thought we were really ready by that time, but then it was really followed by a lengthy commissioning afterwards. So here's the long history. So 2014 we quickly put the detector together, but 2015 entire year was spent on a number of engineering runs to figure out problems. And at the very end of 2015, we thought we were ready to carry the physics running, but then we only ran for 19 days, but then stopped. Not because of the equipment problem, but rather because there's actually a radioactive background which was showing up in the detector. This is the krypton background. Krypton 85 is a beta emitter in the air. You can find a little trace of it. Somehow they get mixed into the detector and called background. So we stopped right after, and then we did a distillation of the liquid xenon, trying to remove these krypton background through the Chinese New Year, and then we restarted in March and ran to the end of June with the first low background results. So this is about 80 days. And starting from July, we kept running. The calibration kept running. So in total, what I'm going to show today are the results in combination of this 30 period and the clean period, in total about 100 days exposure. I already mentioned this is the largest dual-phase xenon experiment producing science data. The major upgrade in this clean period, in addition to the krypton level, we reduce it by a factor 10, is the increase of the exposure and the improvement in the calibration, improvement in the analysis, and also we had a machine learning technique to reduce one of the serious background. All these are a little bit technical. I'll try to skip the details and cut to the chase. So this is a typical what we call the candidate events, or single scatter events, meaning that there's actually just one vertex in the detector, a clean S1 signal and a clean S2 signal, nothing else. And here are the pattern, or charge pattern, recorded on the top and bottom PMP array for the S1 and S2. S2, because of the amplification in the gas, the size of the S2 and the width of the S2 is larger in comparison to S1. Both carry energy information as well as some position information, but position information primarily come from the S2, because actually the light was generated in the gas region very close to the top array. So this picture essentially tells you where in X and Y this event is supposed to be, and the separation between them give you the Z vertex of the interaction. So as I mentioned, we carried out extensive calibrations to study the detector effects. So here is the copper vessel and the liquid xenon cryostat. And this is a TPC, and outside of this we have actually 2 rings of tubes, and you could deploy sources along these 2 tubes. So then you use the radiation leaking into the detector to calibrate. Now this scheme works for small-scale experiment. We started to realize for large-scale experiment, neutron is still okay, but for the other calibration, for the gamma calibration or the electron recoil calibration, such a scheme is insufficient, because the larger experiment will give you more self-shielding, so the outside gamma rays cannot leak to the area that you are interested in. Therefore, for the electron recoil, we had to do something else. So for the neutron calibration, we just load the neutron sources in these 2 rings, and because of the longer mean-free pass is for the order 10 centimeter-ish, you do get neutrons scattered with the liquid xenon causing nuclear recoil. So that's faking the WIMP signal that you can well calibrate a detector. Now for the electron recoil, we have to rely on an internal calibrator. We have to load some tritium into the detector. Not directly tritium, but this is called tritiated methane into the detector. This is actually a technology developed by the Lux collaboration. It was very nice. Once you load it, and circulation will actually mix this tritium methane with the liquid xenon, and then you actually get a very uniform electron recoil, low energy electron recoil background. And then this can actually, because it's hydrocarbon, so you can get removed by the recirculation and recirculation system and the purification system. So let me just show you the upshot between the electron recoil and the nuclear recoil calibration. Now, as I mentioned, the nuclear calibration and the electron recoil calibration differs in the charge to light ratio, S2+1 ratio. So this figure shows the ratio between S2 and S1 as a function of S1. You can view this axis as energy. What we are focusing on is very low recoil energy, below say 10 keV-ish recoil energy. And there are 2 colors. The black is showing the tritium events, electron recoil events. You see S2 and S1 is higher. There's more charge in comparison to the light. And the blue is from the neutron calibration. Okay, so you see they're offset. Of course there are overlap, but one can always say we choose a region where the leakage is small and use that to do the analysis. The typical way of doing this is to actually define your signal region by finding the median of the neutron band and call whatever is below this region the dark matter search region, because that's the WIMP signal, right? More sophisticated analysis will require to do a likelihood fit in taking into account the distribution of the signal in the background to fit your data. And we chose both methods as a test, but the final results was based on the likelihood fit, taking into account the profile of these 2 types of events. Okay, so let me just give you the rate of the low energy rating detector in this clean period. What's shown on the y-axis is a strange unit called rate in milli-DRU. DRU is 1 event per day per kilogram per keV. So it's already a small unit. Milli-DRU is 10 to the minus third. Okay? So this is showing the rate as a function of time in this clean period. One thing that's interesting is that you also see a decline behavior. We analyzed the component in this background. It turns out that at this point we are limited by the intrinsic background from noble gas. One is the remaining krypton background, which is still there. But krypton has a lifetime of 10 years, so you shouldn't see a decline. The other background, which was interesting, was xenon-127. Xenon-127 is not in the stable xenon. So if you have a fresh nature xenon isotope, liquid, you shouldn't have this. But xenon-127 was caused by cosmic radiation. So during the period, we had to send the xenon back from Jinping to Shanghai to do the distillation and put it back. there are 2 months period when everything was exposed to the surface. And because of the cosmic ray radiation, creating a xenon-127. Fortunately, this is only a 35-day lifetime. Therefore, it's decaying away. Anyway, so what you see, this train was caused by xenon-127. It's not super huge. So the dominating piece is in krypton, followed by this. And there's also radon background, another type of noble gas, which is in the detector. So before, for all the smaller detector, background was dominated by the detector material, by the PMT. And in the larger detector, one started to realize that all these noble gas components, they leak into the detector, get distributed uniformly into the detector. They started to become the dominating piece because self-shielding don't help you in this case. They are uniform. Okay, so one thing I want to give you a sense of how small this is. 2 millidRU is actually the world's lowest reported background level. So you see that although with these known backgrounds, we are still achieving the best level in the world. Okay, so now this is a final candidate distribution in position. What's shown here is the 2D plot in Z and R squared. Okay, you're looking at the cylindrical TPC, the event distribution. There are 2 types of dots in here. Each of them is 1 event. The gray is all events. And the red events are events below the nuclear recoil median that was defined by the calibration data. And then there's, so essentially you should focus on these events because they look more like the signal. And the dashed box here indicates the fiducial volume cut. You do need to want to remove all these events from the outside. What you see is, first of all, this gray dot distribution. You do see there's actually a population in the outer part, but as you're going inside, all the background looks pretty uniform. And that's what I was talking about. The noble gas background will just distribute everywhere. And then inside the fiducial volume, there's actually 1 grain data point, which is below the inner median. And that's sort of the final candidate, which dark matter candidate, if you want to say. Inside the spots in total, there are 389 candidates. And the red data points outside are some of the events are physical, and some of these events were due to that they are at the boundary of the detector, the edge of the detector. Sometimes you lose electrons during the drifting, showing up as events look like a background, looking like a signal. But because they are outside, we also remove them. So this is the event distribution for all the candidates, 389. You see, on the same figure of S2 over S1 ratio versus S1, for comparison, the electron recoil calibration medium is shown as the blue curve. So you see that most of them are just consistent with the electron recoil, and the nuclear recoil medium is this red curve, and 1 event is below. Right? So is this a dark matter event? Well, you have to then estimate what is the fraction of these electron recoil background leaking below. So, sorry, this is another figure showing the total candidate in the 30 period where we have a lot of krypton background. You can see 80 days here and 19 days here. There's a lot of more events here, but krypton background is electron recoil in nature. Same figure, we see just 2 events barely below the red line. So do we see 3 candidates in this run? Or you have to then estimate what is your expected background. It turns out that in the screen period we expected 2.4 plus minus 0.7 background, we see 1. So it's a bit of a downward fluctuation. In the 30 period we expect 2.4 background and we observe 2. So essentially everything is consistent with expectation. It's too bad, we wish to see something more, be more interesting, but we didn't see. It's a downward fluctuation background still. Therefore, we could do nothing but set the limit. And I said we set the limit not by doing just the simple cut and counting, but rather do a sophisticated likelihood to the likelihood fit. So what's shown here is our exclusion curve, this red curve in the spin independent cross section versus ring mass. So you see that the minimum point of the exclusion is 2.5 times 10 to the minus 46 centimeters squared at 40 GeV. Okay? And this was a factor 10 improvement just from the run 8 to 30 period along. And in comparison to the previous best reported results from Lux, it's more than factor 2 improvements. So what's shown here in comparison is the final results from Xenon 100 and our results in run 8. Okay. And then shortly after, we actually announced this results in July, and the Lux experiment also announced their results in new results in July, one of the dark matter conference, but we very quickly published in PRL as a cover paper. Just for comparison, the Lux results is shown here with a very similar exposure and very similar exclusion. And then very recently, they recombined their, they call run, early run, 100-day-ish early run, this 300-day later run, combine them together with larger exposure. They reach this black point, which has the lowest exclusion limit at 1.1 times 10 to the minus 46 centimeters squared in the spin-dependent cross-section. But this result is not published yet. But as mentioned, the Lux is already the end of the run, and so this is the best results, and this is the first low background results from Panda 2, and we have additional 500 light days of exposure ahead of us. So also about 2 weeks ago, we released the results in the spin-dependent limits from the same data. Xenon has 2 isotopes. Xenon is 54, so the proton is even, but it has 2 isotopes, 131 and 129, with unpaired neutrons. And because these unpaired neutrons, they have spins, and therefore if wind-path spin could interact with the nuclear spin by actual coupling, so we did the spin-dependent analysis based on the same data, which is shown as the exclusion curve on the WIMP neutron cross-section. Our proton limit is not competitive in comparison, for example, to pico. But the neutron limit is very competitive in all the direct detection. This is the resulting comparison. Lux is the black, and we are the red exclusion for the neutron coupling. And there are some LC contour exclusion band, but that was assuming specific models. And this is the world best spin-dependent neutron limits from direct detection, like I said. Okay, so let me say a few words about the prospect. So Panda X1 and 2 were running in the same infrastructure in a very small area called CGPL, China GP Underground Lab Phase 1. So it's a very small experimental hall with 2 crowded areas for Panda X and the CDX experiment. And now this underground lab is under major expansion into CGPL2. And already there exist 80 experimental halls, brand new experimental halls. Each of them is 14-meter height, 14-meter width, and 65-meter long. Very large detectors. And one of the experimental hall will be the home for the future Panda X program. So we already have this place. And in this larger experimental hall, we will have larger scale experiments, and using these very elaborated shielding is not going to be both cost-effective and powerful. Therefore, we're going to try to enclose all these detectors into a large ultra-pure water pool. What you see here on top of these large water pool, inside of it is a number of detector modules. Let me explain what they are. So this one standing up will be the future multi-ton liquid xenon detectors. In fact, it's not super large. The central region is about 2 meters by 2 meters, so it's not huge or humongous. And there are a few modules lying down, also cylindrical in shape, and these are the high-pressure TPC modules that we envision for the double beta decay experiment. And so we envision both type of experiment will be inside the same shielding to run. Okay, so let me just say one more word about these Panda 3 high pressure xenon 136 TBC. You wonder why we couldn't use the liquid xenon to do the same thing. Liquid xenon also, you could try to do enriched xenon. For example, the programming in the states, the EXO and the next phase Nextel experiment is using liquid xenon to do the xenon 136 double beta decay search. Now, one of the reasons to go after the liquid, the gas, using the TPC technology is that